We're nearing the end of our unit on vector valued functions, and the last concept I'm going to introduce is called the curvature of the position vector, or the position function. The curvature. So I want to show you the definition first, and then we'll look at it in a slightly more practical sense. So the definition is the magnitude of the rate of change of the tangent vector with respect to an arc length, or a length on the curve. Right? Light bulbs are on. Total understanding. No. Sarcasm is engaged. I don't know what that means. So, notationally, what it means is the letter K is used for curvature. So curvature. Notationally, what it means is if you were to calculate the rate of change of the unit tangent vector over an arc length and find the magnitude of that vector, this is basically saying, so how does the direction change over a length? How does the direction change over a length? The problem is S has never been our variable. T has always been the variable. So this is not going to be a derivation video. I'm going to just jump right to the punchline. The formula we are going to use to calculate curvature is going to start with the cross product of velocity and acceleration, which is a vector, and it turns out the magnitude of this vector divided by the magnitude of velocity cubed will give you a rate of how fast does the tangent change over a length. It's kind of a mouthful. Remember, when we have unit tangent vector, that's a velocity over the magnitude of velocity, and the arc length has to do with the magnitude of velocity, so it shouldn't be surprising that some of these components are here. But where did acceleration come from? Not in this video. Well, that can be looked at another time. But this is not a difficult formula to work through. So again, my purpose for this segment is to get you thinking about curvature in a more practical sense. I got a definition that maybe doesn't make sense at all, or just a tiny bit. I've got a formula which the math robot can use to calculate. What's it mean? Well, I have three things I'm going to show you between this and the next segment. And those three things, or we'll call them thoughts, has to do with what maybe we could know about curvature. And so let's get rid of that stuff up here and just look at we have a formula. Could we prove that for a line that there is no curvature? Look, it's a line. There's no curvature at all. Could we prove that it has no curvature? Sorry, no curvature means zero, the number. And then second, for a circle, so circle, the claim I'm going to make is that for a circle, the curvature is constant. It's always the same. If you were driving on a bicycle, you just turn your wheel and you just keep turning left, and it's the same circle the whole time. So my claim is for the circle, the curvature is constant. And then finally, I'll choose one other graph. Let it be a parabola. That for a parabola, the curvature changes. It gets kind of straight at the ends, and it's definitely got a bigger curve here in the middle. And I'm just going to say here, my little description is it's going to be variable. It's going to be variable. This is a perfect place to begin looking at curvature. Could we prove that the curvature of a line is 0, for a circle it's constant, and for a parabola it's variable? So let's start by looking at the line. All right. I'm going to just leave us with a little bit of help here. So this is the parametric equations of a line. Let's put it out here. Line. The formula says I need to calculate the velocity vector. And the velocity vector is going to be 5 and -1 and 4. And if I need the magnitude of velocity, I can calculate that also shortly. The reason I'm not doing that is I want to show you this. Acceleration. The second derivative is 0 across the board. The second derivative is 0 across the board. If I try to use this formula, velocity cross product acceleration, ijk 5 -1 4 0 0 0, I'm going to get 0, the vector, and the magnitude of 0, the vector, is 0, the number. So that means my curvature formula is going to be 0 over something, maybe a square root cubed. But that's going to be 0. The curvature of a line is going to be 0. It doesn't really mean we understand the definition of curvature, but what we believe to be true about curvature should stay the same. Lines do not curve. Lines do not curve. Now, in the next segment, I'll look at the circle and the parabola example. Stay tuned.